So let us continue. Yes, before we discussed the problem with the size dependence of pressure resistance, toughness, or T-crack propagation. It is important also to discuss the size dependence of plasticity. In order to understand this size dependence of plasticity, it is important to look to the real deformation process. The most important is dislocation motion, and since you're mechanical engineers and maybe also civil engineers, they are not so familiar. In order to give a very short introduction to this area, I will try to show what happens when you deform a metal. Plastically deform. If you elastically deform, you simply stretch the spacing between, you change the spacing between the atoms. But when you plastically deform, you do not destroy the lattice. The only thing what happens is that such defects moves in the crystal. So if you deform it, you simply go from here over such way. This was really 100 years ago a big question. How could we deform a metal and the crystal structure remains? And then in the beginning of the 1930s, Taylor introduced this so-called edge dislocation, where we simply have a additional half plane which moves. It is not really the half plane moves, it is only this defect moves through the material. And this is this half plane in a simply cubic lattice. But this half plane, it can also be curved. And then they form this so-called screw dislocation. This was realized 10 years later, or 8 years later, that dislocation not always such a single half plane. It is that also you have, if you go around this crystal, you make here a step. In this case, you have here a missing area. This is the Burgers effect. And all the plasticity is caused by this movement of dislocations. There are millions or billions of dislocations which realize plastic or plastic deformation. Okay, good. This is an important point. So what happens is dislocation moves on specific crystal planes. Yes, and therefore you can see here. This is a microsample and tension loaded microsample, and you can clearly see that these are always a certain number of these Burgers factors, these steps which forms all this. And you see that this part of the crystal is not deformed. Only the deformation only took place on these special planes. And so if you apply continuum mechanics, you can apply continuum mechanics only on this scale, but it makes no sense to apply the stress strain behavior on the scale, which is smaller than typical distances between the slip planes, or where dislocations are activated. I will not go through. Important is there exists a certain stress to move the dislocation. This is the pile stress. Then there is a lot of things related to the hardening of the material. It is a thing, a funny story about this hardening, how to understand hardening. And even I think Taylor made this, or Taylor or Orwell made this comment. The hardening was the first thing what physicists thought to be important to solve, and it may be the last which will be solved. Yes, it's even today not completely solved. Important for the understanding what happens, especially in front of cracks of semi-brittle material also is the multiplication. The most important multiplication process is this ORO1 mechanism. The dislocations are usually, they are pinned between boundaries, dislocation boundary, or between inclusions, second phases, and so on. And when you load up this dislocation, which is always a line, yes, it's always a line, because it must somewhere end. Even if you take out, then this line goes in the depth, then down, again down. So it is always, it must end at the defect, or it must be a closed loop. And this is a mechanism how you simply multiply dislocations. You pull it out, you form a ring, then this part moves in this direction, this in this direction, and you have again the source and it multiplies. So you can multiply the numbers of dislocations. So the density of dislocations varies. If you have a recrystallized material, so if you slowly cool down from high temperature, the typical density of dislocations is 10 to the 12th per square meter. What does it mean? If you take a square meter and you count how many of these half planes you found, yes, on this area, and then you found 10 to the 12th of such defects on 1 square meter. And the mean distance then between these defects, you can simply calculate, is 1 micron. Yes. This is the typical density of dislocations in metals at when they are recrystallized, so when they are really cooled down from high temperature. When you deform, the standard deformed material have a dislocation, yes, about 40–50%. You have 10 to the 14th. So the mean distance is about 1/10 of a microns, or 100 nanometers. So if you look on atomistic with atomistic dimensions, it is not so easy to find them. Yes, there are other techniques, the contrast technique in the transmission electron microscopy, where you can see it much easier. And if you deform it extremely heavy, you come to about 10 to the 16th, but not more. Usually, maybe 5 times or 2 times 10 to the 16th, or not more. Then there exists mechanism where there is a recombination and there's an equilibrium between generation and annihilation of these processes. So in this case, you have a distance, a mean distance of dislocations, which is about 10 nanometers. So every 30, if you go 30 atom distance, you will find one of these defects. In mean, in reality, when you have this high density, then you make they are not homogeneously distributed. They are usually arranged in walls, cell walls, and there are regions where there are less dislocation. So when you, it is now important, especially when you look, if your crack size become very small compared to this length, yes. For example, in semiconductors, the density of the dislocation density is even significantly lower. Yes, it is only, yes, I would say 10 to the 3 or something, or 10 to the 10 to the no, 10 to the 8. So. So the distance between defects is really very large, yes. So, and if you have a crack with a length of 1 micron, the crack will not see any dislocation. Yes, it is so far away that it will not, the loading will not be affected by the dislocations. This is also important when we look then to metals. If our crack comes in the order of microns, then this question, if it is only 1 micron, then I have nearly no dislocation in front of the crack, or the next dislocation is at a distance which is equal to the length of the crack. And we have already seen that the stress the distance equal to the crack length is significantly lower. Yes, it is nearly equal to the stress, to the applied stress. So the dislocation will not see the crack, the stress field of the crack, not really see the stress field of the crack. And if we want now to describe plasticity, that's also important, that we can only describe plasticity in regions which are smaller or which are significantly larger than this length. If we are smaller, then we have a perfect crystal. Okay? And that's important not only for microsamples, it is also important, for example, for fatigue loading. In fatigue loading, especially when we look to fatigue crack propagation near the threshold, the load which we apply are extremely low. Yes, they are, you know, the threshold is in the order of a few megapascal times square root of meter. And in this case, the size of the cyclic plastic zone, if you calculate it, is in the order of micron or below. And if you think that your plastic zone is 1 micron, but in this 1 micron you will not find the dislocation. So what you do is in principle nonsense. Yes? In this case, if you calculate the stress. So in order to do this, you have to really, especially in this, small, if you have heavy plastic deformation, then your spacing is quite small. So it is easier to, or you can use the standard Elasto-Plastic concept with Mises plasticity, even to significantly smaller scale. But when you are in this region where you have only very small dislocation density and very small loads, then it is most probable that you will not find dislocation in front of the crack. So, what happens when, what happens in a metal or intermetallic material, or even in ceramic silicon? What happens when you load? When you load a crack, and if you have no dislocation and no dislocation sources here in front of the crack, it has two possibilities. One of the possibility is that if you have applied a stress intensity which is equal to the Griffith stress intensity, it will fracture. Okay, but we know in most of our metals this doesn't happen. What happens is that the crack tip itself generates dislocation. So the dislocations are generated, and if you hear, this is a pure elastic loaded, simply linear elastic loaded atomic arrangement. And when you carefully look to this line, so if you look here, it looks really perfect crystal. But if you look here, okay, this may be like an embryo of a dislocation. And that's exactly what happened if you load up, and in some of our materials, and these are the ductile materials, the stress intensity to generate the dislocation at the crack tip is smaller than the stress intensity to fracture the atomic bonds here in front of the crack. And that's the reason, that's what we call, from physical or material science point of view, is intrinsic ductile material. They may fail semi-brittle, but they generate dislocation before the atomic bonds are fractured. Okay, and you clearly can see there are only one dislocation. Here's one dislocation moved and one dislocation. This is the same crack. The only difference is that one dislocation moved here and one dislocation moved here. Yeah, that's the only difference between these two. Okay, so that's in silicon at room temperature. There was a long discussion in the 1980s. Is the problem the emission, or that you have also the dislocation have to move? Yes. And there was the discussion: is it difficult to generate the dislocation, or is it difficult to move the dislocation? That's so. But this is a small, tiny thing, and they've finally come to the conclusion it is the problem to move the dislocation away from the tip. Okay. There exist other groups or possibilities that you have, for example, in a heavy deformed material, that you have, if you have sufficient number of sources, then you can again load up, and the dislocation source will activate, and you will generate the plasticity. And the first group, this is this type of simulation we have done in the 90s. One of my first or third doctoral student, and at approximately the same time, the group of Needleman van Giesen performed exactly the same simulation, but with one difference: they don't assume generation of dislocation. They only placed a large number of sources in front of the crack, and these sources are generate dislocation, and then the crack can grow by, in their model, by a decohesion similar as in the Griffiths concept. The only thing which is necessary is that the dislocation sources must be activated before you reach the Griffiths toughness. Otherwise, it would fracture. That's the trick behind this thing. So to describe the fracture process of these, let me say now, semi-brittle materials or plasticity, it is small dimensions. We know when we come to these small dimensions, typical Mises plasticity becomes senseless. One of the things what continuum mechanic groups have done is to use crystal plasticity, where they take into account really the single slip processes, but even this crystal plasticity concept cannot be used on this scale. They can only be used on scales which are large compared to the spacing of dislocations. And they cannot describe, for example, the size effects. You will come in a few seconds. They cannot describe, because it is a continuum mechanic concept in the standard version. If you take then into account a gradient, then you can also come to a size effect. They can introduce a size effect. The next, which really can tackle this size effect, are this discrete nature of mechanic of discrete nature of plasticity. But this discrete nature of plasticity can describe the growth of the evolution of plasticity, but it is difficult to describe then even the separation process at the crack tip. These can only describe the fracture process. Then you have to take further assumption. Another possibility is then to go even further, to go to molecular dynamic. But molecular dynamic has the disadvantage that it's really limited to very small volume. Yes, you can, even today you can use 1 million of atoms, but 1 million of atoms is not so large. Yes. If you look to a cube of 1 million atoms, there's are only 100 atoms times 100 atoms times 100 atoms. That's not more, and that's not much. Okay, and if you go, and even this molecular dynamic are rather limited because the potentials which you use, because you simply assume that you have points with a certain potential, with certain laws of which depend on the distance of the atoms, yes, of cohesive forces, and the real description, you have to go to density function theory, the quantum mechanic. But in this case, the maximum atoms are about 1,000, yes, maybe 2,000 if you have really enormous computer power. But in this case, the only thing what we have already done, we have sometimes used this, is to calculate the stress which are necessary to move the dislocation at 0 Kelvin, or to look to the structure of the dislocation or something. You can do. But it is not possible to really describe plasticity in a unique way on this scale. That's an important point. And that's also the problem why we cannot describe the fracture in a simple way, in a unique simple way. One has to take this always into account. We have to simplify our view. Okay? So, when we now, for this consideration of the stresses, the dislocation, from the dislocation mechanic point of view, is the simplest one, because it is really analytical. You can analytically describe the stresses in distance of nanometers. Yes, when you realize plasticity, for example, in mode 1, mode 2 loading, this point means that you have edge dislocation, this screw dislocation to realize a mode 3 deformation. So why you can do this is if you, this is now crack, if you introduce, or if you omit 2 dislocation, what we have done here before, in this case, like in this case, yes, can really calculate the stresses which are caused by these 2 dislocations. And these are the tension stresses induced by the 2 dislocations. Here is 1 dislocation, and here is 1 symmetric. And the interesting thing which this figure should show is that this dislocation induces near the crack tip a stress field which is exactly the same stress field as you would load the crack. In this case, it is a compressive stress. So it means that you would compress the stress. Or in other words, if you generate here these 2 dislocations, and you apply a external stress, you get the stress field, and the 2 dislocation reduces the stress field. That's the effect of the plasticity, exactly what happens. But really, near the crack, the stresses can be in the order of near the theoretical strength. And they are not, if we go to nanometer dimension, then the stresses can really, here these are for 20, I think, I don't know why this image shifts. Okay, so when we have a dislocation, when we generate dislocation here, and this dislocation are usually, especially if they are generated at the crack tip, the distance of the dislocations are in the order of few 10 to 100 nanometers, yes, typically. And if they are generated at the crack tip, they form a zone which is nearly free of dislocation, few 10 nanometers. And it is interesting that you can really describe by linear elastic tool, not with linear elastic description, the stress at the crack tip, and the stress at the crack tip is simply given by the applied stress and stresses induced from the dislocations. These are exact linear elastic solution. This is an exact linear elastic solution from the loading. It is exact linear solution from the dislocation. And since in linear elasticity, there exists a superposition principle, and you simply can superimpose all the things. And it is, in principle, we could describe the plasticity in front of a crack on discrete dislocation mechanic. The only problem is that we would have to take into account all the dislocations which are generated. Yes, this can be millions. And the description of the plasticity is very similar to the description, for example, of the arrangement of our universe. Yes, if we know all the masses distributed in our universe, at the speed of all the masses, it is very easy to calculate what happened with this universe. Yes, because we know the gravity law, we know the law, the simple Newton laws, and that's else. We have not to do more. The only problem of the persons in astrophysics is that they do not really know the exact distribution of the masses. Yes, but in principle it is not difficult. Yes? And the same problem have we in our case. And the problem is that so many dislocations are there, and only for, I would say, in 2D we can treat about 2,000, 5,000 dislocations. Yes, what you have seen here, for example, these are few hundred, but in principle, a few thousand would also be possible in 2D. In 3D, it is. You have to separate this line into small pieces. There exists also exact solution, what is the stress field of these small pieces, yes, of dislocation. And the only thing what you have to do when you calculate is, you simply look to the position of the dislocation, you look what is the stress caused from the external loading, and what is the stress from all the other dislocation, all the other pieces of dislocations. And then you know, okay, the stress, the dislocation can move or cannot move. That's all. So in principle, the calculation is simple, but it is simply a problem of power. So this is now here, you see what happens when we load up. In this case it was a mode 3 crack, but for a mode 2 crack is exactly the same. The only difference in the equation is here, 1 minus the Poisson ratio is different. If we load up, then we generate the dislocation here in front of the crack. And this is the stress field of the dislocation. Yes. And this is the stress field which causes the stress field, the change of the stress field at the crack tip. This is a so-called shielding stress intensity. And in the near vicinity of the crack, you can describe again the stress field by a local stress intensity factor, which is simply the applied stress intensity minus the stress intensity caused by all the dislocation. That's very easy in principle. So when we look, for example, here there are 9 dislocations generated, and if we look carefully, then we see, okay, here there is 1 dislocation, next, and so on. We see the singularity in the vicinity of the dislocation. We have also a singularity stress field, and so if we would really measure the atomic displacement, we would see this stress field, yes, with except the distance is smaller than the dislocation. It makes no sense. And this is exactly what we would also, from continuum mechanic point of view, we would expect this behavior. Yes. But in reality, we have this variation of stresses. They are enormous high, yes, can be enormous high, even in the case of plasticity. Yeah. That is what we always should take into account. If you assume a low strength material, you assume that the stress is very low at the crack tip. But that's not true. The mean stress is low. Yes. The local stresses can be in the order of the theoretical strength. And you will never have a debonding of atoms when you are not in the order of the theoretical strength. That's what you should always take into account, yes, when you look about fracture. So this is the typical scheme which we use when we discrete dislocation simulation. In this case, we have always a stress field from the applied loading. If the dislocation is in the vicinity of a free surface, we have also to take into account that this, the stress field of the dislocations are only simple for infinite size. And, but it is easy, if a free surface is there, you can take into account by image stresses. And this stress, if this stress is larger than a critical one, then a dislocation moves. Here this is for a mode 3 or mode 2 crack. The equations are not very difficult, yes, which you use. And what we have done in the 90s is to understand the threshold by this discrete, the threshold of for fatigue crack propagation by this discrete nature, because at these very low load amplitudes, the numbers of dislocations are quite low, so that classical continuum mechanics cannot be applied. What we have done is simply, okay, we load up, generate dislocation. If we unload, few dislocation will roll back, and they form new area, and in the next sample, next loading cycle, it will happen the same. That's really the process in ductile materials. You see, this was the results of discrete dislocation simulation. You see the arrangement of dislocation, and the crack is grown, and it forms some serration, some special shapes. Okay, I will show you one thing. This is what happens when we load, for example, a crack. It's really taken into account only that you need a certain friction stress that the dislocation can move. If you unload the crack, dislocation moves back. They form this V-shaped crack. If you load again, dislocation moves again away from the crack end. If we assume that the surface cannot revolt, the crack grows by this process, and it really shows that the crack growth behavior in the discrete dislocation simulation is really very similar to what we really physically observe. This is here now for the crack is now grown. The crack is now grown over a certain distance, about a few microns, and now what happens is also shown. So this is a cycle. This is after 1,000 cycles. Now the scale is varied. This here is in units of Berger's factor, or you can assume in units of lattice spacing. Yes, plotted. This scale is different to this scale, therefore you don't see this V shape of the crack. But what you clearly can see that the crack, we have the emission of dislocation. It runs back, and it really reflects what happened really at such small load. Okay, so and interesting to see the size. These are, well, let me go back. This here. These are 30 microns. This would be, if we have a coarse-grained metallic material, this would be more or less what happens in one grain. So this would be the arrangement, the necessary arrangement of dislocation. I will not go into detail, this would be another thing. But what you clearly can see, there are distances where these are nearly dislocation free, and where really always more or less linear elasticity can be applied. Now let us come to the size effect. This is very strongly related also to the discrete nature of plasticity. The first, yes, not really the exact first, but really very popular, become this area of size dependence in the 1990s, where Fleck and Evans have performed some key experiments on wires and bending beams with relative small dimensions. Yes, here you see the wires with 100 micron and 12 micron. They here plotted here a normalized yield stress. And what you clearly can see when this was always the same material, when you reduce the diameter, you significantly change the yield stress. It looks like a complete different material. But when you perform the same thing with the tension experiment, the differences are quite small. And the same was in the case of bending. So here they perform bending experiment as a function of the applied strain, and they looked here to the necessary flow stress, normalized flow stress at the surface as a function of the surface strain. And also they could really see that the flow stress significantly increased, decreasing diameter. And this was one of the paths that in continuum mechanics they introduced the so-called strain gradient theory. But the question was now, can we use this strain gradient? These are samples in the region of from 10 to a few hundred microns. Can we use these strain gradient theory also to smaller dimensions? Because we have seen that the mean spacing of dislocations are typically 1 micron or below. In this case, the sample size is large compared to the mean spacing. Okay, the question is now, can we use this strain gradient theory also to smaller dimension? So, this is now a nano indentation experiment, and you see the enormous change of hardness here as a function of the size of the indentation size. In reality, it falls even further. But for this case, you will see this later. We have to use a logarithmic plot in this area. So the standard, most used concept to explain this size effect was also the strain gradient theory. This results in the so-called Nix-Gao model. And I always had some doubt on this, that this really works for these extreme small dimensions. And so we performed really careful experiments. The idea of this Nix-Gao model is really simple. Yes. The idea was, okay, when we increase the plastic deformed volume below the surface is always proportional to the size of the indentation. That's the idea. And in order to realize this shape, we need a certain amount of dislocation, because in order to make all this shape change, we have to move dislocation here downward. Yes. Or there exists different arrangement, but in all the case, we need a certain number of dislocations, yes, to realize this. And if we want to pack this in a certain volume, we have a much denser arrangement of the dislocation when the indent is small compared to a large. That's easy to calculate when one do this. And if one take this then into account with this strain gradient concept, then which is more or less based on this already in the 1913th introduced concept by Taylor, that is dependent on that the yield stress is proportional to the square root of the dislocation density, and then there exist statistical stored and really geometrically necessary dislocations. These are also the base for the strain gradient theory, because in order to realize a strain gradient, you need geometrically necessary dislocations. And if you do this, then you come to this relation. And if we plot this really careful measured over a very high range, then we see that this do not work. And what we also have done is to look to the arrangement of the dislocation below the indenter, and what we have found is that it is this principal assumption that this deformed volume is proportional to the size is not true. In small deformed volume, the dislocation are more widespread than in the case of large indents. And therefore you have a different gradient or different geometrical arrangement of the dislocation. And this goes to this relative complex change of the hardness as a function of the indentation size. And what you really see is that the hardness of your material here, when you go of this single crystal to the largest values, can be very nearly 1 order of magnitude. It is exactly the same material. It's a perfect single crystal. Yes. And even if we would go to even finer, smaller crystals, we would come to higher values. So plasticity is extremely size sensitive when we go to dimensions of below 100 nanometer. But when we look to the separation processes in brittle or semi-brittle material, then we are in this area. Yes. Exactly at the same time, beginning of 2000, there were another story coming up. This was the so-called micro pillows. The most prominent, unfortunately, we have applied for our FIP in 2000, 5 years before, but we couldn't get it in our first approach we need. And this was approximately 1 year, the same year where we got our FIP, and therefore Eugene was somewhat faster than we. He measured the strength of a different type of materials as a function of the diameter in a compression experiment. And you see the enormous variation of the yield stress as a function of the diameter. Here you see a summary of the results. Again, here the size. And this also clearly indicates that strain gradient cannot be explained why we have this increase in yield stress. There was really a big discussion about 10 years ago that we have a compression experiment where we assume that we have homogeneous stress distribution in this area, yes, and we get a yield stress variation of, again, more than 1 order of magnitude. Yes. So, what should we do? Okay. One of the things for this large effect is, what we thought at this time is, that one of the large effects is the dislocation. They can maybe move here free, but the problem in a compression experiment, they cannot run out here at the top. If they run into the surface, it is difficult. So they cannot pass through the whole sample. And that's a problem with compression experiments. But it's a compression experiments, the most simple one if you make small samples, because it is very easy to fabricate such a pillar, yes, with a focused ion beam. Therefore, we started with our tension experiment. It was the first tension experiment. And what we have done is now to simulate this. We have changed the length of our sample, the really necessary, the deformation length of our sample. We have always the same dimension, okay? And what we can see is that even this volume, the length of these, dramatically affect the yield stress. Nearly a factor of 2, yes? That's enormous. Because it is not so surprising, because we have here dimensions, that's are the typical distances where dislocation moves, yes? And therefore it is not so surprising that the yield stress in this dimension changes in such a, over such a distance. And here I have tried to summarize what we have done. These are the compression experiment, this pillar experiment. It shows really a pronounced size effect. These are the tension experiment with what we call standard tension sample, where the thickness is 1/5 of the length. That's our standard dimension. And this is when the length is smaller. Then we come more clearly to the compression. And one of the things is that this dislocation moves on plane, and only when the dislocation planes over the whole length on free surfaces, then they can really move freely. Otherwise, they are constrained here, top surface or the bottom surface. And this makes or induces significant constraint and induces significant size effects. And this is, if you look then, for example, to semiconductor components, where you have dimensions of metal films in the order of microns, which are within a surface which are attached to silicon, maybe above is an oxidation layer. And we have these dimensions, and you cannot simply use the yield stress of kappa. That's senseless. Or when we look here, if you look to, for example, for a medical device with small dimensions, which are mainly banded, for example, or for flexible electronics, which are also mainly banded, you see that the yield stress of these kappa changes again from 200. This is a really macro, and this was not the onset of yielding, it was really, I would say, the plateau strength during the yielding. It is 5 times higher. And the reasons is relatively simple for it. Why banding is, we have not studied over such a large distance in the banding as in the tension experiment. The reason is quite simple. If you generate a dislocation can move in a certain direction. But at the opposite side, the shear stress is in the opposite direction. It cannot move further. Yes? Only the dislocation can move it somewhat above. So the neutral ax in the bending beam is somewhat like a barrier for the dislocation, like a grain boundary or phase boundary. And therefore, in the bending experiment, the yield stress is significantly high. This is a typical experiment, what we have done. We've done the first of this type in the beginning of 90. But then, here you can see, one could do this in a 2D experiment. Oh, it's not working. Why? It's not good. Why? Let's try again. Oh yes, now you can see. This is now really 3D calculation. 3D, MD, or discrete dislocation simulation. In 2D, I thought that you can really realize relative large plastic deformation, but they do not reflect the real plastic physics. They reflect some of the effect of discreteness of plasticity, but not all. And for this, you have to take into account really the 3D nature. These lines, what we have seen, these dislocation lines, they are curved. And when you make this 3D calculation, you have to take all small parts of this and to look what is the effect of these small parts on all the other dislocations. Yes? And you have to do this for every movement step. And that makes the limitation for this discrete dislocation. What you really can see is that all the dislocations are stored here in the center and piled up to this neutral axis. Okay, so when we talk now about the yield stress or the fatigue strength of metals, we have also seen this for fatigue experiments. As a function of the sample size, here we have taken a logarithmic scale. And if we are in the area where the microstructural size is very small compared to the diameter of our sample, then we are in a size-independent region, yes, for plasticity, for the yield stress, and also for fatigue properties of the material. But when we come into a region where the dimensions of our sample becomes in approximately the order, if we 5 to, yes, we have seen so 7 to 8 times the grain size, for example, then it is interesting that the strength go down. That's a simple effect that the surface of the plasticity is not as constrained as in the interior. It is quite easy because, yes, in the surface, deformation can do what they want to do, but here at the boundary between to the next grain, plasticity cannot do what they want to do. They have to adapt with the neighboring grain, the plasticity. And therefore, we have this decrease in fatigue strength and also the decrease in yield stress. And when we come then into region where the size of the sample is smaller than the crystal, then we get again a significant increase. This increase depends on many different things. It depends on the constraint. But one of the reasons, even at very long crystals, single crystals, there exists a very simple reason why the yield stress increase. You need a source for the dislocation generation. In this coarse-grained material, the size of the source is simply limited by the grain size. And here, the size of the source is simply limited by the size of the sample. That's not really difficult yet. But the real behavior is difficult. Okay. So let us start with some points before we stop here. The ductile fracture. We come then to the semi-brittle of micro-sized dimensions. So ductile fracture is, in our material science point of view, is the generation of pores, the growth of pores, and finally the coalescence of the blunted crack with the pore. Yes, that's ductile fracture. And when we talk about ductile fracture, we have always the discussion, what is the stress state in front of the crack? And Then we always ask, what is the stress state at the crack tip? And what is the stress state in larger distance of the plastic zone? This is also important when you go to the semi-brittle process, yes? Because semi-brittle fracture may occur in the whole nonlinear region, whereas ductile fracture mainly occur at the crack tip. Okay, when we look to the effect of the stress state, we have only the simulation, and we have only the simple solution for plant stress and plant strain. The real intermediate is more complex, but this is the situation. In the elastic case, in principle, in the elastic case, the stresses in the loading direction and in the growing direction are exactly the same. They are not affected by the stress state. The only difference is that in the plant strain case, in the direction perpendicular to or along the crack front, sigma z, the stress is 2 times the Poisson ratio times the stress in the loading direction. And there is one difference also between plant stress and plant strain. It is, if we recalculate the energy release rate, there is this small difference. As in the plant stress case, in the plant strain case, the energy release rate is somewhat smaller than the energy release rate in the plant stress case. This is simply due to the relaxation, the relaxation in the thickness direction delivers more energy for crack propagation, because in the thickness direction, in the plant strain case, the volume elements cannot go back to the unstrained case, and therefore there is this small difference. But that's the only difference in the case of elastic loading, of the effect of stress state. But the effect of stress state in the plastic zone is enormous, especially if we go very near to the crack tip. And this is especially important in thin films and also in microsamples. In really macrosamples, it is very difficult to realize a stress state, plant stress state. You can realize a plant stress state here at far distances from the cracks, but it is nearly impossible to realize it very near the crack. But in microsamples and in thin films, you really can also realize relative near to the crack tip a plant stress state. In the Elasto-Plastic case, very near the crack tip, which means that we are looking here very near to the crack tip. This is the HRR solution. This is the region of the size of the planting. The HRR solution do not really describe the stresses at distances which are equal to the size of the crack tip opening displacement. But at larger distances, it describes quite well. So, but what we see is that the stresses in the tension direction is now 3 times the yield stress. In the crack growing direction, it is about 2 times the yield stress. And in the stress parallel to the crack front, it is about 2.5. That's a rough estimation. The reality in hardening, you see, it goes somewhat above 3. And if you take into account hardening, this is only for non-hardening material, but very simple estimation for this, but really good. And in plant stress, the stresses are significantly reduced to about the yield stress. It was it's very simple from the consideration. And this enormous difference, 3 times the yield stress between plant strain and plant stress, makes this enormous difference between a plant stress dominated fracture experiment and the plant strain dominated fracture toughness experiment. What happens often in thin samples. To realize now what happens when we look to materials with different toughness values or different sizes, because if it is not possible to look separate only to effect of size, you always have to take into account what is the toughness of the material, because the toughness of the material describes the amount of loading which you can apply. Yes. In the case of a linear elastic, in very small loading, the size effect is extremely small. If you reduce the thickness to smaller than to the size of the K-dominated zone, no, if the size is smaller than the K-dominated zone, the thickness, then you have the this is the plant strain case. All dimensions are larger than Rk. Then you have this equation for determination of the energy release rate. And if P is small compared to the size of the plastic zone, then you have to take the plant stress solution. When we go to the small scale yielding case, where the plastic zone size is small compared to the dimensions, then you come, and also the thickness is small compared to the plastic zone size, then you usually determine in the ductile fracture case a size-independent fracture toughness, a size-independent crack growth behavior, fatigue crack growth behavior, or size-independent creep crack growth behavior. But when the thickness of the sample come into the order of the size of the plastic zone, then we have usually this increase in fracture toughness. But when the size becomes very small, then it goes down and can be significantly smaller than the fracture toughness. I will show you then some example that the fracture toughness can be really significantly smaller than the fracture toughness of a material in the macroscopic plant strain tests. And when we go now to elasto-plastic fracture mechanic, when we look to the elasto-plastic fracture mechanic, what we know from elasto-plastic fracture mechanic, where the crack tip opening displacement is, when we go to this, when the crack tip opening, the planting of the crack, or here, when this crack tip opening displacement is significantly smaller than the thickness of, in the old standard it was about 25 times CTOD, now in the new is 10, but 10 is really a bit tricky. This initiation of crack is independent of the size, because the fracture process zone is within this HRR dominated area. But what happens is that this so-called tearing modulus is really significantly size dependent. And if also the thickness become smaller than the CTOD, 10 times CTOD, then all the dimensions affect the fracture toughness. Okay. Yes, I think you're hungry. Oh, let me see. Maybe. Yes, let me look through this very fast. This is a ductile semi-brittle material which we recently have investigated. It's amorphous metal. amorphous metal film, or amorphous metal glass film, pure silver, and amorphous, such a multi-layer structure with dimensions of 50 nanometers. Yes, and what I want to show here is that this phenomenon in the micro dimension, especially in lamellar structure, can be quite different. This was the sample. You have seen this the macro sample, and we bend this and fracture this. This is the notch. Here we see that the first crack propagation starts because the brittle zirconium fracture, but the metal makes at first such bridges, and finally we get some crack propagation through this film. It looks macroscopic like a brittle fracture, but what always happens is you get a necking of this very tiny silver films. And the result was quite surprising. We could not understand at the beginning what happened, because we thought, okay, we should have the size dependence, like what we have here. We should have an increase when we decrease the thickness of the sample. So we have studied different sample thicknesses from 3 micron to 500 nanometer. Yes. The size of the plastic zone is in the order of 200 nanometers or something like this. And what we usually would expect, this behavior, what we know from our sheet material, or all our sheet materials with millimeter dimension, within 5 minutes. But what we have seen is, it was exactly the opposite. You get a decrease. Yes? And the reason is relatively simple. Yes? What is the reason for this increase in ductility? The reason for this increase in ductility is that in the plastic zone, in front of the crack, most of the volume elements are under blunt stress condition when we come in this region. Yes, this increase. The generation of pores is strongly affected by the tension, the stress in the tension in the loading direction. And we have seen that in blunt stress, the tension in the stress in loading direction is significantly smaller than in blunt strain, and therefore the formation of pores is shifted to significantly larger strains. We can load up the sample to significant larger strains. Only in the interior of the sample where blunt strain takes place, we have some crack propagation. And then in our sample, it is now different. In the very things, what we have is, and also the growth of the pores is significantly reduced in the blunt stress case, because in the blunt strain case, we have enormous high stresses in the loading direction, in the thickness direction, and in the crack propagation direction. And this causes a nearly, spheroidized growth of the pores very fast. Whereas in the blunt stress case, also the growth of pores is significantly retarded. Therefore, the crack tip opening displacement under blunt stress condition is significantly larger in this case than in the blunt strain case, the critical crack tip opening displacement. But this is not the case in our samples with this fine lamellar structure. The critical crack tip opening displacement is determined by the thickness of our silver layer, which is simply necked. So it is about 25 nanometers. You see, or 30 nanometers. The crack tip opening displacement is not significantly affected by the thickness of the samples. And if we simply calculate the crack tip opening displacement for and take the stress intensity, is the stress intensity divided by the yield stress times the elastic modulus and times a value which depends on the stress state. And for the blunt stress state, it is about 1/2, yes. For the plant stress state is about 2, and for the plant strain case, plant strain case is about 2, and for the plant stress case, it is about 1. And therefore, you can clearly understand why we have this change of the, because the crack-tip opening displacement in our micro-lamellar or nanolamellar structure is not changed by the stress state, which is in most ductile material the case. And therefore, we have this different behavior. And then the next example will I show tomorrow. Okay. Good.